Hi everyone. In today's video, we'll be creating a Bitcoin trading strategy. I thought it was a really excellent breakdown on how to set up a notebook for any kind of data science project, but specifically if you wanted to explore how to pick a model for price prediction, etc. Um, so this trading strategy came from this GitHub repository here, who ultimately pulled it from this Machine Learning and Data Science Blueprints for Finance by Hariam Tatsat, who also happens to be the author of this repository. He's a quant author, an ML and AI enthusiast. So go ahead and give his repository a star and keep watching his content. Because I think it's really valuable, the sort of tutorials that he provides in these chapters here. There's one specifically that we're going to be looking at. I've just called it the Bitcoin price prediction, and I've made it work here on the Google Colab library. There's quite a lot of computation that's involved. So I've already ran through all of the cells, and I'm just going to go through the code and highlight areas that I have changed either to make the notebook or make the predictions work or make the models work, and update his trading strategy here in this book. So without further ado, let's just jump into it. First thing you're going to need to install is SkyKeras. He does use this these packages here. He wants to use the Keras classifier, and typically this is done through keras.wrappers import Keras classifier, but that's been deprecated, and you can get the same basically Keras classifier just through SkyKeras. So the first thing you want to do is install that. You're going to install the regular suspects. You're also going to import almost all of the sklearn modules that I've ever used, and you'll see why a little bit later on. Also get the Keras to do some deep learning examples. I mounted my Google Drive because the data that we're using was provided in the GitHub repository. It's a complete history of Bitcoin, but it looks like it's pre-2020. So I'm using just a set CSV that's been taken along, that was collected a long time ago. This might work better for an updated version. You could probably pull even more historical data, etc. It wouldn't really matter. The columns that we're interested in are the timestamp, open, high, low, close volume, volume currency, and a weighted price. So you could create your own data set, but I wanted to replicate as much as possible the performance of the model in the example. So I went ahead and used the same data that was used in the repository. To prep the data, we're going to forward fill the values in the dataset columns. We're also going to drop timestamp because in this example, what we're doing is trying to classify a price signal for when basically the short moving average is greater than the long moving average. So we compute this by taking a rolling window of 10 for the short and a rolling window of 60, take the average of those, and those become our long and short moving averages. The signal then becomes 1 for a buy, and that's where the short moving average is above the long, etc. So we're trying to predict in this instance what kind of values create a buy signal, right? So the data set sample, I just took random sample of 5, and you can see here we have the open, high, low, close volume, volume currency, weighted average, and then we've added on our signal and short moving long. Great. We still want to do some additional feature engineering. In a previous video, I talked about how doing a feature feature importance analysis, as well as reducing the number of features in your data set, can actually be beneficial. And one thing about feature engineering on the flip side is that you can calculate a bunch of technical analysis to increase the amount of features and dimensionality on your data set. And from this, you could probably get some really interesting insights. And this is true even of non-financial datas. But part of data wrangling is making sure that you have all the data that you need. So in this instance, we're going to calculate exponential moving average. And I'm not going to go too deep into it, but we just create a function that calculates that for us. And then we create an EMA 10, EMA 30, EMA 200 just by passing in those values through the data set and setting that to a column, right? We also do that with the rate of change. And the rate of change, obviously, it's not that complicated. You can see it here, but we also just pass in those values and we take a rate of change of 10 as well as a rate of change of 30. We calculate momentum, both 10 and 30. We calculate the RSI, which is a little bit more complex here, but this is basically just the calculation or the formula for calculating RSI. And then we create a RSI 10, RSI 30, RSI 200. We add that to our data set. We also create a stochastic oscillator. Anyone who's done a bit of trading probably has seen a stochastic oscillator feature in their research. Something if you use TD Ameritrade or Charles Schwab, I've definitely seen this, where you can set a stochastic oscillator setting. But we just create a function to calculate that for us. And then we also create a moving average. And we use the stochastic oscillator to calculate several different important, more features basically. And then we calculate moving averages of varying degrees as well. So you can think after all of that, if we take a sample of our data set, we now have 29 columns. So we've increased the size of our data set. This is 29 columns. I believe originally we had what? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we had 9 columns and we increased it by 20. So to reiterate my point in previous videos that I've made, if you have a 29-dimensional shape, it can be very difficult to calculate the movement of that shape or the movement of a plot point within that space of a 29-dimensional space, right? Computers can do it, but it's very difficult for even the human mind to sort of comprehend how does a data point move in a space that has 29 different dimensions. So you could see how the complexity of that dimensional space makes it more difficult for our model to actually be accurate in its predictive analysis. So the next step is once you've wrangled all of the data that you're interested in, that you think is relevant to your project, the next step here would be to explore it, to see exactly what kind of this data is telling us. The way I was taught to do EDA, exploratory data analysis, was you start with a univariate plot, a bivariate plot, trivariate plot, and you just keep going up from there until you're doing a multivariate plot. In this instance, in the example given here in the repository, he did a weighted price at graph. And I've seen this graph before. You can kind of tell this is the beginning of Bitcoin. And we can kind of see that this is where it really started to take off like crazy, right? It's probably nowhere near this. We know it's dropped pretty dramatically since then. But this is basically the price that we see. You can also do a histogram plot of each of our features to see how those features are sort of weighted. So you can see that it's in terms of the high open, low close, Almost all of the values are weighted on one side over another. They're not evenly distributed. You can see that we have several columns that have just one or two classified values. This one, almost all of the data is concentrated in the middle of these graphs here. This is sort of an interesting graph. There's more on the ends here, and then it goes back up in the middle. And this is another sort of interesting one. It's very highly concentrated on the ends here, but it dips in the center, right? Another thing that we'd be interested in looking at, the signal, this is sort of giving it away by highlighting the signal, but the signal is the feature we're trying to classify. And when you have a classification problem, especially if it's between a 1 and a 0, or just two different classification values that you can have, you want it to be balanced. So one thing that you would want to do is take a look, maybe create a bar graph and see, are my signal values balanced? And this is relatively balanced. It's not 100% 50-50, but it is relatively balanced here. Okay. Another thing I've mentioned in previous videos is it's really helpful to take a correlation and create a correlation matrix on that so that you can see what features are highly correlated to one another. This is a really good example of that. So you can see here, this is our correlation matrix. And I know if we look at some of these columns here, the values are really overlapping, but that's why it's color coded so that we can understand whether or not it's correlated or not. So blue indicates that it's less correlated. Red indicates that these two features mapped together are highly correlated. So you can see we have big chunks of red here that are super highly correlated. So open, high, low, close. It is a 1-to-1 correlation with one another. So you got to ask yourself, does it make sense to have 3 or 4 additional values or features in our graph that are this correlated to one another? Because if they are, it might actually make predicting our signal skewed, might not actually make it accurate because it's inputting data that doesn't hold much predictive value as an individual signal or as an individual feature, I should say. Not to confuse our actual signal feature here. So when we looked at this graph, we said, okay, MA 21, 63, and 252 are really highly correlated with open, high, low, close. So let's get rid of some of these columns to reduce our dimensionality and to make sure that each one of the columns that we're passing through our model actually holds some predictive value that doesn't overlap with another feature that holds the same predictive value. So we dropped the high-low open volume currency, and in the example given, you dropped the short moving average as well as the long. I probably also would have dropped the MA 21 moving average 63 and the annual moving average. But in this instance, I wanted to stay as relatively true to the tutorial given. Okay, after that, I just took another sample. This is just to show that we went from 29 to 23 after we took out some data sets or data columns. Excellent. So now we're on to the exciting part. We can do the model train testing aspect of the tutorial. And I thought this is really where the value comes in because I haven't seen too many tutorials in my sort of journey learning data science that sets up a boilerplate method to test several models in a way that allows you to really pick the best one for your particular project. So in this instance, we just calculated, what would be, we just want to take the first, what is this, 100,000 values or rows. And from that subset data, we say we just want the signal column to be our Y. Our X is going to be all the other columns that are not the signal. Validation size is 20%. We're setting a seed of 1. This is just to create reproducibility And then we train test split it into our X train, X validation, Y train, and Y validation. We have to pick some values to begin with. The issue with this is that these values are random at first. So we're just saying we're going to do a tenfold, a seed of 7, and our scoring is going to be based on the accuracy. And then what's interesting is that what Mr. Tatsat did here was he placed all of the models from logistic regression, linear discrimination, KNN, decision tree, Gaussian, MLP, Eta Boost, Gradient Boost, and Random Forest. He just appended all of those models. He initialized them and set them all in a list. From the list, he did a K-fold and a CV cross-validation on each one of those. And this is where the most computing took place. I think it took about 30 minutes to run this cell here. And you can see at the end of it, we have all of our models in our list. We have the results. And then we also have the cross-validation standard deviation score as well. So you can read here, they all scored pretty well, but the GBM and random forest models perform the best here. And we can actually plot that using a box plot. This is a really big box plot, but basically we have our models on the x-axis and we have our performance here on the y. You can see the random forest scored the best, etc. So to remind those of you who might not be familiar with K-fold, it's going to be difficult without a visual explanation, and I highly recommend looking up a video on K-fold if you're not familiar. But what this method does basically is it breaks up your data set into an equal number of parts. And the idea goes, if I did this manually and I said, I want to train my model on the first 80% of my data and test on the last 20, well, someone really smart came along and said, well, is that last 20 that we're testing on really the best subset of our data to test the performance of our data on? And so what K-fold does is it splits up our data into equal parts. In this instance, we set it to 10. And so it split up our data into 10 sets, and it tested our data on each one of those different subsets of 10. So basically, you don't want to test your data on the same training data because obviously you're going to get wildly inaccurate results. But what K-fold does is it says, okay, I'll train you on the first 9 out of 10, and we'll test on the last of the 10 out of 10. And then the second round, it'll retain that score, whatever the score of that model was, and then it'll go through it again. But instead of testing on the last, 10th segment, it'll say, well, let's test on the 8th out of 10 segment, and I'll train you on the other segments. And it'll do that for each of the 10 segments. So it's calculating the average score of 10 different training and test methods, testing, whatever you want to call it, and then it holds that value. So then we did that for each model that we put in our list here. So that's what we're seeing here. We're seeing the average accuracy results of all of our tests as it's been split up 10 ways of our data set. Now, I know that doesn't make much sense. Trust me, it's a really good way of honing in on the accuracy. It's a good way of, it's really not so useful if you're just doing it on one model, but since we've got several models here, it's a really good way of testing which model in our list is most accurate for our personal project. So you don't have to do 10. You could do 3 or 4 or 5, but I think 10 is sort of the standard just the standard that the industry uses. Okay. This isn't a video about K-fold. Maybe I'll make one later if people are interested, but let's move on. So what we realized from this methodology here is that the random forest classifier is our best performing model, so we're going to use that. We can continue to tune the model. We need to figure out what are the best N estimators and depth, as well as what is the best criterion for our model to even make it even more accurate, even better, right? So pretty standard stuff here. We scale it. We then take that newly scaled data and we say, is it better to have, N estimators between 20 and 80 or 5 and 10, criterion of Gini or entropy? And we do basically a grid search where we test these different parameters of our model and we run through it again. And finally, at the end result of that, we have basically our grid result, which has been tuned, and we are now ready to create predictions. So we run through that, and at the end of it, we say, look, you got the best result using the criterion Gini with a max depth of 10, using 80 N estimators. So we say, okay, we're going to plug that into our model. We're going to initialize our random forest model using the N estimators and the jobs that we've done in our tuning up here. And then we're going to fit it to our X-train and Y-train data. We know that the random forest classifier is probably the best model to use. We know these are the best parameters to use given our grid search. And when we then create predictions on our validation data, you can see here that we have a precision of 90%, 91 here, recall 89, F1 score 89. So, right, we're doing really good here. We're scoring above 90% on predicting the signal features of our data. And we can visualize this with a confusion matrix. Confusion matrix is really handy for classification. It's basically saying the actual result of our validation test set for one, our model predicted this many times. So it's very blue. So most of the time it was classifying correctly what it was given. So we do have a few false negatives as well as some false positives, but nevertheless, our model has performed very well. Okay, great. So we then take a look at the feature importance. So now that we know that our model is performing really well, we want to ask it, so what features are you using to make these predictions so accurately? And we see here that the RSI 30 was the greatest feature for predicting the signal of our buy or sell on our strategy. It does have a few other features, but the close, the weighted price, the volume, these data sets are not as important. And this is actually something I've seen in other research that I've done. Interestingly, the high-low close volume sets are just not as important as I originally thought. So then we can backtest the data. And basically what we're doing here is we're creating a new data frame. We're putting our predictions into that data frame. We're creating columns for that. We're creating columns for our signals, the actual returns, the market returns, and we're calculating the percent change to come up with those data points there. And we take the CumSum historical. So we're going to take the histogram of the strategy returns versus the actual returns. And then we're going to plot it over one another. And this is where you're really going to see how well the strategy did versus the actual returns. And you can see that the strategy had a slight edge over the actual returns of the price. So what is the actual price? The actual returns of this would just to be buy and hold versus our strategy price, which is trying to predict the, every time that it predicted where a buy signal was, that's where we calculate our prediction, right? Or that's where we calculate our returns on that prediction. So what we're saying here is each time we correctly identified a buy signal, we're charting that as a return. So you see that there's a slight edge there, and it's pretty interesting. It's not dramatically better than the actual returns of just buying and holding, but you can see that through all of that, we can be fairly confident that we're at least going to follow the market returns. And not only that, we're going to have a slight edge on the market returns as well. This is something that you could automate, etc. Obviously, I am not saying go out and implement this. This is mostly just me showing you how to set up a data science project to investigate a strategy and um, how to really robustly choose a model as well as uh, tune that model for a really effective outcome. This is really one that I haven't come across a whole lot of tutorials out there that is this thorough on making sure that we're choosing the right model as well as hyper tuning it for the best performance that we can get. So I hope you found this interesting and enjoyable. I sure did. And I will see you guys in the next video. Take care and see you in the next one.